Hello and welcome to my battery monitoring engineering comparative analysis series, video number 3. And I want to start this video by going back and clarifying the discharge rate information that I provided in video number 2 for the BACS Generex system. Now Dan Bailey, the CEO, sent me some information clarifying their discharge rate, which is approximately 200 to 250 milliseconds per BAM or battery module, and it's all on the same timestamp. So that means that the controller is sending out this information and then receiving and essentially collecting all of it and putting it into a discharge module report. And you can clearly see that from the report that he sent me here, that the discharge rate to include that delay from the controller to go out and extract that information is approximately 2 seconds. So if we compare this to the EMSIS system, which I have right down here, you can see it in front of me, the normal update rate for nominal voltage capture under a discharge is approximately 3.3 seconds. Now you can modify this. That's the amazing thing about the EMSIS system. You can verify, modify, or change any of these different parameters. That's the empowerment from the manufacturer that you do not receive from many other of the big box manufacturers. So you can modify that all the way down to a much faster scan rate. But I want to overview why this is an important fundamental concept to understand, because as you increase the discharge rate that is being captured from the battery module, what that's going to do is there's a parasitic load from that module because it's being powered off of the battery. So if you increase that discharge rate capture, you're also going to increase the current draw from the battery module. So that is not a negative consequence in these systems because they're also rebalancing or reconditioning the batteries at the same time, but it does increase the current flow through the entire battery string. And if you have one of those battery modules fail, that could be a negative impact on the system. But thankfully, again, it's reporting out via SNTP an alarm condition if one of those things fail according to the pre-programmed thresholds that you set up during initial commissioning standards, okay? And the second part of this video, I wanted to review going over some of the new products from EMSIS, which is really amazing. They have a new wireless AC monitor, and it's amazing because it'll help trip AC mechanisms, but it also has a relay for DC current for thermal runaway protection that I want to overview. It's fantastic. They have some incredible advancements and improvements in their system. But before I go, let's overview something that Dan sent me that I thought was fascinating. What they did was they looked at a comparative system from the Albert or Vertiv versus their BACS Generex system. And I haven't overviewed or highlighted this in detail, but essentially what it is they had 2 different discharges that they reviewed and compared from each one of the systems, and they wanted to see if the parasitic load that Albert and Vertiv likes to say in their marketing materials that many of these battery monitors that are powered from the battery may imply or infer onto the system actually doesn't impose a negative consequence, because it's effectively rebalancing or reconditioning the voltage of the battery much more effectively than the Albert or Vertiv, because they're not doing it. So you actually see an increased capacity from the systems that are running on the BACS, and the EMSIS would fall under the same premise on this guideline. And that's very important to understand in regards to what these systems are doing. Not only extending the life, but increasing the capacity drive and the characteristics of an electrochemical generating device is amazing. It is a fascinating and an extraordinary achievement. I can't wait to dive more into some of this R&D. Keep sending me more information. So let's dive into the wireless current transducers and the relay and a wireless battery monitoring system that you can just clip on from EMSIS. We'll dive into that now. We'll also go over from a fundamental aspect how current transducers operate, and we'll go into that now. Thank you so much. Let's get started. Hello and welcome back. Now, Hall effect current transducers are utilized everywhere in data centers and critical infrastructure. They're in PDUs, they're in UPSs, they're in generator systems. All of the circuits throughout the data center and critical infrastructure utilize these types of Hall effect current transducers, but more specifically in battery cabinets. We need to install and configure these types of systems because they help us mitigate thermal runaway type mechanisms in a battery cabinet versus installing a shunt. You can do the same thing with a shunt, right? But you have to install it in series with the battery cabinet, which means you have to disassemble it and install it across the anode and cathode. They're usually quite large for power dissipation purposes. So this is much easier. And again, we want to connect that to some kind of an external relay, and then the normally open or normally closed contacts of the battery cabinet terminal, which you can then connect to the UVR or shunt trip mechanism of the UPS. But let's review how this system works really quick. It's very basic and simple. Now, Hall effect current transducers allow non-contact detection of direct current and alternating currents using a Hall element, a magnetic electric converting element, okay? And CTs are either open or closed loop. This is open loop, and they measure AC and DC currents and provide electrical isolation between the circuit being measured and the output of the sensor. The primary current is measured without electrical contact with the primary circuit, providing galvanic isolation. Now, open loop current sensors consist of a Hall sensor mounted in the air gap of a magnetic core or conductor would go through here, right? And that conductor is going to produce a magnetic field comparable to the current, and this magnetic field is concentrated by the core and measured by the Hall sensor. Now, the signal from that Hall generator is so low, it needs to be amplified, and it is this amplified signal that becomes the sensor's output. Open loop sensors normally have circuitry that provides temperature compensation and or calibrated high level voltage output, okay? Now, while they have a definite price advantage over closed loop counterparts, their downside is that they can be prone to saturation and temperature drift. That's why they need to be recalibrated on an annual basis most time, or if they have an auto calibrate a feature via constant current source, they can do that internally in the system. Now, again, this drift can be minimized to some extent by injecting a positive coefficient or constant current source, as I previously discussed, in the control circuit to reduce the drift and the sensitivity over the temperature. And the great thing about EMSYS is they have a wireless relay, and this system is called the WRL400, and this provides a way to remotely disconnect the power supply to the UPS. And this is a key component and element of the EMSYS battery monitoring systems to prevent and mitigate thermal runaway entirely. Now, one of the great things about their software is you can use the EMSYS web configuration application to remotely disconnect the breaker manually. So if you see something that's not exceeding the pre-programmed threshold, but you're wary of it, you can just go in and trip the breaker yourself. And if you have 5 different battery strings, it wouldn't, impact your redundancy, your parallel redundancy for your runtime. So this is really amazing for this type of system. And again, these are all powered off of the battery, right? So I believe it's 12 to 60 volts. You want to try to connect it up to 60 volts. That'll reduce the current draw and spread it out and distribute it across those battery systems. But this is an amazing thing of the EMSYS system, because let's say you wanted to install a thermal runaway protection system, but you were limited by budget. You didn't want to put battery modules on all the batteries, but you just wanted to have a contact relay system, normally open, normally closed, which is what they have, that wireless relay. I'll put it back up here so you can see it. And then just one CT. So now you're just measuring flow current. You can put an ambient temperature sensor in there as well, maybe in a couple different spots of the battery cabinet, because usually the temperature differential is higher at the top. The heat will rise than at the bottom. It's not always that case. Depends on the airflow through the battery cabinet, how it's designed. But it's very important to understand. So very simply, you can have a few temperature points in the cabinet. This wireless relay, which is receiving current from this wireless sensor, and no battery modules at all looking at the individual voltages of the battery, but purely looking at the current and temperature. And a low-cost thermal runaway mitigation protection system can be easily devised and installed. And again, I could teach my 6-year-old son how to install some of this stuff. And that's one of the biggest advantages that EMSYS has over everybody in the market. All battery manufacturers that are looking at the monitoring systems, installing one of these wireless based systems, all the 40 modules, as long as the tab washers are installed, is as simple as going up and plugging it into the anode and cathode. And I really, really applaud Dragon and Marco and their entire team for continuing to iterate and improve all of these individual processes of the software to empower the end users. It's really important. But also, as we come back to another product that they have that Dragon and I spoke about several years ago, I think it's really amazing. It's not a CT anymore. We're going to jump over to a wireless battery monitor. Dragon and I were on site 5 or 6 years ago, and I spoke to him about creating a battery monitor that you could just clip on with alligator clips, which is really a necessary evil on data centers, because a lot of battery systems that you come upon do not have tab washers installed. So let's say you wanted to do a discharge test, a performance test, a capacity test, or you just wanted to troubleshoot and isolate a battery that's looking like it has a low state of charge, maybe it's going in sulfation, it's at 12.8 volts or something like that, you've equalized it, it's not coming back up, you can clip this system online right here. It's called the CSPY-400-L, and that is their Cell Spy LITE wireless battery monitor. Dragon, you were listening, I applaud you, sir, it's fantastic. But this makes it much easier to go in and install a system without, having to adhere to EEW permits, IEEE standards for safety mitigation. You can just go up and clip it in as long as you have all your PPE on. According to the arc flash, studies that are posted on the battery systems, it's usually quite high now. It's actually it equates to the AC arc flash as well. They did that several years ago. It's very important to understand, okay? But this system's amazing. So now, if you wanted to do a thermal runaway system or maybe just monitor a few batteries this way, this gives you much more flexibility in installing things at your facility. And again, they empower you with the software. So you have access to the admin portal. You have access to the the software running on the applet. You can run it up on your cell phone. It basically plugs into all mobile electronics, iPads, cell phones, all the way across the board. It's exceedingly fast. I love it. It's really amazing. And their last product, which I think is groundbreaking, it's revolutionary, is a wireless AC current monitoring system. Very similar to that other relay, contact relay, but now it's looking at AC breakers, not DC breakers, right? And this is called the Breaker Spy. And according to them, it's the most advanced AC current transducer in the entire market. And what's really amazing about it, it does not, and I'll put that up here so you can see it, the installation is exceedingly simple. All you have to do is install it around a conductor, and it'll power right off of that conductor, which is fantastic, right? If you think about it, it has a dual functionality as a circuit breaker monitor and a current measurement tool. So I'll throw some of those analytics up here from the software, which shows you how the system works. Now imagine having this in your system where now you have a bunch of battery monitors, like 2,000, 3,000 batteries, 10,000 batteries, but you also have a bunch of older breakers that require monitoring, and or tripping mechanisms. And this Breaker Spy, which is around 15 millimeters, it's incredible, will allow you to do that. And again, it can be powered off an internal battery, or it can use the electromagnetic field of the cable of which it's installed, which is, again, a fascinating development and improvement in these kinds of systems. And again, you can power them off an internal battery. I believe it's a USB 5 to 16 volts, or you can power it off the electromagnetic field of the battery. The range is around 0 to 200 amps, resolution is 0.06 amps, accuracy of about 1% or better, and they think that's for the ACCT-200-15, and then they have an ACCT-200-10, which has a range of 0 to 50 amps, and a resolution of the same 0.06, and an accuracy of around 1%, and all of these communicate with a wireless spectrum. We will call that the frequency ISM band, 2.4 gigahertz at a DSSS range indoor of just around 50 meters, and you can expand that out with expandable external repeaters, and you'll need that in certain environments that have a lot of noise, which I discussed in video number 2. So I hope this kind of enlightens you a little bit with many of the advancements and improvements in the industry. I did want to reiterate and clarify that scan rate issue yesterday from BACS and Generex. Thank you, Dan Bailey, for sending me that information. I'm not infallible. I'm always updating and reviewing, the things that I say and the information that I know. And I can tell you this, the more I learn, the less I know. It's a powerful premise. So always returning back to many of these educational videos and then updating them is very important for you, but it's also important for me because I understand that I'm conveying the highest level mastery of information and knowledge and wisdom in regards to battery monitoring systems and IEEE standards and the data center community as a whole to you out there, and that's very important to me. Thank you so much for tuning in to video number 3 today. I sincerely appreciate it. If you have any questions, please never hesitate to contact me. Hope you have a wonderful day.
In closing, I thought it might be helpful to visualize looking at the coup de foie, the tail of the whip, the discharge curve, and the data points as they're being captured in 16.6 milliseconds versus 250 milliseconds or 1 second. So let's take a look at this really quick. We're going to have a discharge curve here. This is the battery normally charged, and as it undergoes a discharge, it's going to come all the way down, and then there's going to be a release point here, and it comes all the way back up and starts to recharge. Now the Albert or Vertiv system is capturing every 16.6 milliseconds, so there's data points all over the place, very, very quick refresh, like a raster scan, all the way down, and then it's going to basically capture all these data points all the way up, and it depends on how you have it set up in your pre-programmed thresholds, either on a current magnitude, so it'll capture discharge if it's greater than 5% full scale of 600 amps or greater than 30 amps, or if you have it configured to set up and record on a voltage recapture, which means it'll capture the entire discharge curve and the voltage recovery or charging mechanism, because sometimes batteries fail right here, okay? Now, if we take a look back, and let's take a look at the same kind of mechanism for the BACS system, and we're looking at the discharge curve. So we're going to do the same thing again. We're going to come down and go all the way up and come all the way up there, okay? So 250 milliseconds would be like here, and then here, and then here, and then here. So you can see the difference. The resolution is decreased, but again, at 250 milliseconds, that does meet the IEEE specification for discharge current, and it is much faster than what I stated at 5 times for the entire discharge. The EMSA system can be pre-programmed all the way down to 50 milliseconds, but you're going to pull more current from the battery at that point. So it's important to understand that, okay? So I hope this understands that you can kind of see basically the 16.6 millisecond system, right? And that's what we're looking at for the Vertiv, and that would be versus, and we would bring that all the way over here, 200 milliseconds for the BACS system, and then the BACS can be pre-configured. So if you look at that, the difference between 150, 250 milliseconds, and then much closer data points all the way through, you can see the difference. You can see why some organizations prefer having data points all the way up. But again, if you're able to record the discharge curve at 5% full scale for all of your system, plus the recharge voltage all the way out, I mean, that's the more comprehensive way of looking at these systems moving forward. I hope this helped you guys understand and visualize the capturing of data in the discharge curve, and I really appreciate you tuning in to video number 3. Have a great day.